The next topic that we are going to cover is how to combine resistors that are connected in parallel. We're going to do so by analyzing this single node pair circuit now. So whenever we have a single node pair circuit, that means that all of the elements are connected in parallel. And so they all share a common voltage. So I'm going to go ahead and label that common voltage. I'm going to call it V. And I'm going to assume that the positive polarity is on top and the negative polarity is on bottom. I'm making that assumption because my expectation is that this current IS that leaves the source will come and enter this node, and then it will divide itself among all of these parallel connected resistors. So the current is going to be flowing down through each of these resistors, which means in order for them to be absorbing power, the voltage needs to have positive polarity on top and negative polarity on bottom. I'm going to assign each resistor a current. So with resistor R1, I'm going to have some resistor current IR1 direction down. With resistor R2, I'm going to have a resistor current IR2 direction down. And with resistor Rn, I'm going to have a resistor current IRN direction down. Now, I'm going to write a Kirchhoff's current law equation where I am going to say that the currents that are exiting the top node are positive and the currents that are entering the top node are negative. So my Kcl equation should look like negative IS plus IR1 plus IR2 plus IRN. I can isolate the source term and put it, this is equal to 0. I can isolate the source term and put it on its own side of the equal sign. So I'll have IS is equal to IR1 plus IR2 plus IRN. And now I can use Ohm's law to express all of those resistor currents in terms of the common voltage V. So using Ohm's law is equal to V is equal to IR, I can say that I is equal to V over R, and from that I get V divided by R1 plus V divided by R2 plus V divided by Rn. There's a common factor of V in all of the right-hand side expression, so I can factor that out, and what I'm left with is V multiplied by 1 over R1 plus 1 over R2 plus 1 over Rn. And so I see that the current source doesn't really see the individual resistances. It just sees an equivalent resistance Req, comma P, where the subscript, comma P, is being used to illustrate that all of these resistances are connected in parallel. So we can do just a little bit of algebra and relate this term, 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Rn, to this 1 over Reqp, and we find that Req P is equal to 1 over R1 plus 1 over R2 plus 1 over Rn, and this whole quantity, we take the inverse of it. We could also write this using summation notation as Req P is 1 divided by the sum from I is equal to 1 to n of 1 divided by R sub I. So, finally, we can create an electrically equivalent simplified version of this circuit by simply having our current source, IS, connected in parallel to our resistance REQ, P, and observe that the same voltage drop V occurs in both circuits.